change the way you look at things, and the things you look at will change. What do you think about changing the way or the point of view freely while watching a video stream? Hello everyone. Today, my colleague Rajab and myself, Maria Sarkis, fourth year telecommunications engineering student at ISAC, will be presenting our project entitled Free Viewpoint Television. In the next couple of minutes, we will be talking about FTV. First of all, what is FTV? Then we will give an introduction about the ray space. After that, we will go through the transmission scheme to get deeper and talk about the correction, encoding, compression, and 2D, 3D display. Jad, the floor is yours to tell us what is FTV.
Thank you, Maria. Television realized the human dream of seeing a distant world in real time and has served as the most important visual information technology to date. However, TV shows us the same scene even if we change our viewpoint in front of the display. Although many important technologies have been developed, this function of TV has never changed. That's why the concept of FTV is introduced. FTV stands for Free Viewpoint Television, and it is based on ray-space methods. This innovation is a visual media that enables us to view a 3D scene by freely changing our viewpoint as if we were there. And as I mentioned before, that the most essential element of visual system is not the pixel, but the ray. Maria, can you tell us about the ray-space method?
Of course I can. The ray space is a virtual space. However, it's directly connected to the real space. The ray space is generated easily by collecting multi-view images while giving consideration to the camera parameters. A ray in general can be mapped to a point in the 5D ray parameter space, since every ray is parameterized in space by its location, represented by XYZ coordinates, and by its direction, represented by phi and theta coordinates. Now for FTV, the main two types of ray space that are used are the orthogonal ray space and the spherical ray space. As we can see in the right-hand figure, it represents the orthogonal ray space, where a ray is expressed by the intersection of the ray and the reference plane, and the ray's direction is as shown in the figure. On the other side, the other picture represents the spherical ray space, where the reference plane is said to be normal to the ray. Furthermore, the orthogonal ray space is used for FTV with the linear camera arrangement, whereas the spherical ray space is used for FTV with the circular camera arrangement. The linear camera arrangement is used for parallel view, and the circular camera arrangement is used for convergent view. Now, Jad will provide us with an overview of how the transmission is done.
We'll talk about the sending and the decoding processes. The sender side, a 3D scene is captured by multiple cameras. These captured images contain the misalignment and luminance differences of the camera, so they must be corrected to construct the ray space. These corrected images are compressed for transmission and storage by the multi-view coding encoder. Now at the receiver side, reconstruction of images is obtained by the MVC decoder. The ray space is constructed by arranging the reconstructed images and interpolating them. Free viewpoint images are generated by cutting the ray space vertically and are displayed on a 2D, 3D display. Now let's get deeper in the correction part. As you can see in the two figures, the geometric distortion of two-dimensional camera array is corrected by the affine transform. It's seen that the trajectory of correspondence point becomes square by the geometric correction. And now, Maria will be presenting information about compression.
First, we have to understand why the data should be compressed. So as mentioned earlier, the same scene can be captured using several cameras. This means that the video frame contents are highly correlated. That is, there is a high level of redundant information that can be removed through encoding. This step is very important because the system has serious limitations on data distribution applications. such as broadcasting, multimedia streaming services, and other commercial applications. That's why we need to compress the multi-view sequence efficiently without sacrificing its visual quality significantly. The multi-view video coding standard, or MVC, builds on the intercoding techniques that are applied across a temporal sequence of frames in single-layer video coding to extract the redundancy between the two views of 3D video. More specifically, MVC typically first encodes the left view and then predictively encodes the right view with respect to the left view. Now, one approach to streaming the MVC encoded 3D video is to transmit the encoded left and right views as a frame sequence with twice the frame rate of the original video. That is, left view of the first video frame from first capture instant, then the right view of the first video frame. After that, the left view of the second video frame, then the right view of the second video frame, and we continue so on. And since the right view is encoded with respect to the left view, it is typically significantly smaller in bytes, here we say, and the sequence of alternating left and right views result in high traffic variability, as you can see in this picture. Note that there exists another encoding alternative that consists of downsampling the left and right views to fit into one frame of the original video resolution. And here, the pixels of left and right views are horizontally subsampled to pixels so that they fit side by side into one frame. This side-by-side approach permits the use of conventional 2D video coding and transmission systems, but require interpolation at the receiver to obtain the left and right views at the original pixel resolution. Now, Jad will give us a description of how the video is displayed.
FTV needs a new user interface to display free viewpoint images. There exist two types of display. We have the 3D display and 2D 3D display with a viewpoint controller, or used for FTV, which stands for free viewpoint television. However, there are two problems. We have a limited viewing zone and discreteness of motion parallax, because the width of the viewing zone for each view approximates the interpupillary distance. The view image does not change with the viewer movement within the region. On the other hand, when the viewer moves all over the area, the view image changes suddenly. Due to this, viewpoint control by head tracking are invented to solve the motion parallax issue. To sum up this discussion, FTV is an advanced visual system till now. And here a question can be asked. How can we integrate artificial intelligence in this visual system to make it more intelligent in the future?
With this, we end our presentation. Hope you enjoyed it, and thank you for your attention.